The true genius of invention is the solar panel. Shine light on it and it generates electricity. Sunlight is the fairest and most abundant resource on Earth. As long as the sun rises, we have an inexhaustible source of energy. The key is that the principle of solar power is incredibly simple and clever. Before understanding how it works, let's grasp a basic concept. Electric current is essentially the directional movement of electrons. With that in mind, let's dig up some sand, refine it into 99.999% pure silicon crystals, and then polish and slice them into thin wafers. These silicon wafers are the core material of solar panels. But pure silicon doesn't conduct electricity. Silicon is a tetravalent element. Imagine each silicon atom as a monster with 4 hands, each gripping an electron. These electrons are shared with neighboring silicon atoms, tightly bound and unable to move freely. To make silicon conductive, we need to dope it, replacing some silicon atoms with pentavalent elements like phosphorus. Phosphorus has 5 hands, meaning it has 1 extra electron that isn't held by any neighboring atom. This free electron can move around, creating what's called an N-type semiconductor. If we apply an electric field, the electrons will move directionally under its influence, forming an electric current. However, in reality, when sunlight hits an N-type semiconductor, photons give electrons enough energy to break free, but without an inherent electric field, their movement is random and chaotic. No current is generated. So what's the solution? Next, we dope another silicon wafer with boron, a trivalent element. Boron atoms have 3 electrons, meaning one of their hands is empty, creating a hole. This hole can snatch electrons from neighboring atoms, making the structure a p-type semiconductor. Now, if we combine the n-type and p-type semiconductors, we form a p-n junction. At their intersection, something interesting happens. The extra electrons from the n side flow into the holes on the p side. Once they combine, they stop moving, creating a depletion layer that blocks further electron flow. Electrons accumulate on the n side and holes on the p side, creating a strong electric potential difference between the two. If we connect wires to both ends, electrons will flow from the negative, or n side, to the positive, or p side. Current is born. As sunlight keeps shining, electrons in the p side get excited again, breaking free from holes. The built-in electric field pushes them back to the n side, creating a continuous flow of electricity. In an actual solar panel, the sun-facing side is the n-type semiconductor, while the back is p-type. To allow more sunlight to penetrate, the n layer is made very thin. Since a single solar cell only produces about 0.5 volts, multiple cells are connected in series or parallel to increase voltage and current. To protect the cells, the outer layer of the panel is encapsulated in transparent plastic, which insulates and filters harmful UV rays. The top is usually covered with tempered glass for durability, while the back consists of multiple layers for physical protection and heat dissipation. The generated electricity is then fed into the grid, powering homes everywhere, and that's how solar panels work. Did you get it?